Section 5.3, double integrals in polar coordinates. Now, learning how to do double integrals in polar coordinates is going to save us a lot of time and a lot of pain, potentially, when we start to integrate over general regions that can't really be partitioned into nice, neat rectangles. First, let's do a quick recap on polar coordinates. Rather than using an x and a y axis, for a polar coordinate, we'll use a polar axis, and we'll have a polar origin. Polar coordinates start by setting a length, the radius, so some distance along the polar axis, and then you allow that to rotate some angle theta. Positive angles rotate counterclockwise, and once you rotate that radius, you can mark the end of it, and that's how we describe points in polar coordinates. Now, we are more comfortable with Cartesian coordinates because we've seen them a lot. And so often we'll translate between polar and Cartesian. So we'll translate from r and theta back into x and y, and vice versa, x and y back into r and theta. It's not that we're moving a point around at all. We're keeping a point fixed exactly where it is, but we're describing it either by the x and y vertical and horizontal coordinates, or we're describing it by the polar r and theta. Now, rectangular partitions are great for rectangles. If you take a look at the blue and green partition that I've created on the screen, assuming we're looking at some x and y Cartesian plane, this rectangular region that I have outlined in white fits really well on this rectangular grid. But if we wanted to replace that region with something that wasn't shaped so rectangular, we might have a problem. Notice that some of these grid spaces aren't complete rectangles, so we wouldn't really be doing a great job at partitioning our region if we tried to keep things rectangular. So instead, let's try and describe that region using polar coordinates. So just like we partitioned each of our independent axes in the xy plane, we're going to do that for the r and theta values in the polar plane. So I have marked out different constant values for a radius, so different arcs for radius going from 1 and continuing up. And then I'm going to do the same thing for theta. So I'll partition this region over fixed values for theta. And notice that we've created these nice partitions that fill up our polar region perfectly. Now, these partitions almost look rectangular, but they are not perfect rectangles. Remember that the blue lines are arcs. So if I exaggerate this a little bit, you can kind of tell this is not a rectangle. We call it a polar rectangle. But if we're going to use polar rectangles to partition a region for double integration or iterated integration, we're going to need to know how to write that area increment dA. In rectangular coordinates, dA was either dx dy or dy dx. But what about in polar regions? So if that dA area came from multiplying length times width for the area of a rectangle, we need to come up with the area for a polar rectangle using our delta radius and delta theta. The way we're going to do this is by breaking down a sector. So if we start off with a large sector and then we remove a smaller portion of that sector, it's the polar rectangle that we're looking for that's left behind. So in order to do the area of a sector, you need to know the angle that the sector spans, and you need to know the radius. Using the formula 1/2 theta times radius squared, we can calculate the area of each one of these sectors. So we'll calculate the area of the large sector, we'll calculate the area of the small sector, we'll find the difference between them, and that will give us our polar rectangle. Now, because we want the polar rectangle for partitions, we're going to describe all of our areas right now using the same reference point, this r sub k is the center of the polar rectangle. So let's assume that that r sub k is perfectly centered from left to right and from top to bottom of our polar rectangle. So, and then we're going to describe the large sector using theta, so our theta spans. And then our radius is going to be described by that rk start value plus the remaining part of the sector. So if rk is perfectly centered, it's halfway through that polar region. So we can describe the total radius of the large sector as rk plus our delta r divided by 2. So we have everything we need to do the area for the large sector, and then we can do the same thing for the small sector. They do need to have the exact same theta, otherwise we would be left over with something different than a polar rectangle. So both of our sectors have the same delta theta. The radius will be different for the small sector though. Instead of rk plus delta r over 2 to get the remaining portion of our large sector, we're going to subtract delta r over 2. That way we can come back to the smaller radius. Now we have everything that we can use to calculate the small area as well. And so we have those displayed on the screen. Each one of these sectors is described as 1/2 times delta theta times the radius squared. Now this is where our algebra skills are going to come in handy. We're going to simplify this the best that we can, and the result is going to be our formula for our area of the polar rectangle. So after all that algebra, we're able to see that the area of a polar rectangle looks like the r sub k, that center of the polar rectangle, times the delta r, so the length between that smaller radius and the larger radius, times delta theta, so the angle that spans from side to side. So, that being said, instead of saying dx dy or dy dx, our polar partitions dA will be replaced with r, dr, d theta. Now this is really important to pay attention to because it's not simply dr d theta. There is an extra factor of r, and if you forget that, you'll get the wrong answer. So we always have to remember in polar partitions, the area increment is calculated with r dr d theta. All right, now that we know how to partition a polar region, let's practice integrating in polar coordinates. So first thing we always want to do is sketch our region. The polar region R that we're integrating over contains all of the points R and theta such that R is between 1 and 2. So if I'm thinking about a polar region, I've got my polar axes. Let's say r equals 1 is along this line, r equals 2 is along this line, and theta is allowed to go from 0 to pi. So I need to extend my drawing because pi is all the way over here. So the region that we are integrating over looks like a rainbow or a half a donut or a half a bagel, however you want to describe it. So here's our region that we're integrating over. And the integral that we're working on is a double integral of the function 3x dA. Now, as this is written, we don't have a nice, neat expression for bounds on x and y, which is why using polar coordinates is going to do a great service for us. We're going to replace dA with r, dr, d theta. And then if we're going to start to integrate variables r and theta, the function that we are integrating needs to be translated into polar coordinates. So 3x, if we convert it to polar using x equals r cosine theta, 3x becomes 3 times r cosine theta. So the double integral becomes a double integral of 3r cosine theta times the area increment r dr d theta. Now I do have two factors of r in here, and it's perfectly fine to write those together, so we could write this as 3r squared cosine theta dr d theta. And now we just need to apply the bounds to our integrals. dr is first, so we'll put the bounds for r. Looking back at the set builder notation for our region, we see r is allowed to go from 1 up to 2, and theta is allowed to go from 0 up to pi. And then we just integrate as usual. So starting with r, we can integrate 3r squared cosine theta with respect to r. Well, 3 cosine theta looks like a constant when we integrate with respect to r. So we get 3 cosine theta r cubed, and we need to evaluate that between r equals 1 and r equals 2. Let's simplify the factors of 3. So we're really looking at cosine theta times r cubed, where r gets to go from 1 to 2. That's going to look like cosine theta times 2 cubed minus 1 cubed, or 2 cubed is 8 minus 1 cubed, that becomes 7, so we get 7 cosine theta. And then we need to integrate that over our theta region, so theta is from 0 to pi. We're integrating 7 cosine theta d theta. And the integral of that is 7 sine theta. Remember, we're evaluating theta from 0 to pi, so 7 sine pi minus 7 sine 0. Sine at pi is 0, sine at 0 is 0, so our final result is 0. Now remember that double integrals can be used to represent volume. So essentially, we just found that the volume underneath the function 3x over the region R, that half disk, the total volume came out to be 0. And the reason why that happened is because the volume above the xy plane, or the polar plane, and the volume below the xy plane, or the polar plane, they were equal. And so the symmetry in the problem canceled them out. So that's an issue with net signed volume.